So in this video, we're going to start talking about the notion of span and linear independence. Although I don't think we're going to get to linear independence in this one. Um, in any case, up until this point, we've been talking about vector spaces in the abstract. The time has come to start trying to do some kind of calculations in these vector spaces. And this brings us to the notion of a linear combination. Sorry, maybe we should start with a definition, as we always should do. Given vectors v1 through some vn inside some vector space v, a linear combination of these vectors is any sum where the AI belong to whatever the field is that the vector space is over. Maybe I should say for all I, if I want to be really precise. In any case, let's take a look at some examples of this. So first off, let's take two vectors. We have 2, 1, minus 3, and 1, minus 2, 4. These are both vectors in, they could be in complex vectors, but let's put them in R3 just to make it kind of easy because, they're evidently having real numbers. Now, we can ask ourselves whether or not any particular vector is a linear combination of these two. So here we have a question. Is 17 minus 4, 2 a linear combination of, and let's call this one v1 and this one v2. And let's see if we can figure this out. So first thing is we often don't say this. What we would say is that 17 minus 4, 2 as a vector lies in the span of v1 and v2. Span is by definition the set of all linear combinations. Kind of squeezing it in on the end, but I think it's okay. All linear combinations. And so we'll often just use this terminology instead. It's the title of the video. And now how do we figure this out? Well, what we're asking is there some A1 and A2 such that if I call this guy W, that I can solve this, right? And I can work out an A1 and A2 such that A1 V1 plus A2 V2 equals W. Well, what does that actually entail? The easiest way is to remember that we know how to multiply scalars times vectors. And also we know, oh, sorry, I copied down the complete wrong thing. That's totally not right. It should be 2, 1, minus 3 plus A2, 1 minus 2, 4. Okay, it's right now. So we know how to multiply. We get 2A1. Let's write it this way. Plus, not plus, 2A1, comma, A1, comma, minus 3A1, plus A2, minus 2A2, 4A2, equals this thing. And we know that if these are going to be equal, then after I combine these component-wise, right, 2A1 plus A2, A1 minus 2A2, minus 3A1 plus 4A2, this is actually just a system of equations. In other words, what I'm saying here is I have to have the following equations be satisfied simultaneously. 2A1 plus A2 equals 17. A1 minus 2A2 equals minus 4, minus 3a1 plus 4a2 equals 2. And so we saw in the last video how to solve systems of equations like this. Okay, in that video we had x's and y's. Here I have, and z's. Here I have a1 and a2, but it's the same process. 2, 1, 17, 1 minus 2 minus 4, minus 3, 4, 2. And then we're going to try to do the Gauss-Jordan algorithm on this thing and see if we can see any solutions. Now, one comment I want to make as I'm going through this is that those of you who are super familiar with this already, or you've seen Gauss-Jordan before, you guys know that when I have more equations than I have variables, we don't expect there to be any solutions. And that's very reasonable. You know, when you're thinking geometrically, the collection of all vectors in V that can be achieved by taking some linear combination is we can kind of draw it, right? So like here is maybe R3, and then you have two vectors. And I'm not going to try to draw this accurately because these vectors are complicated. But let's say that you have like a V1 and a V2, right? And so you can make like this plane, right? Right, of all combinations, things that you can get by adding and stretching and taking combinations and so on. Why would some random vector, like any other vector that's not in this plane, right? You're not going to be likely to find some combination that does it unless you have enough degrees of freedom to do so. And that's kind of what this is measuring, is we're asking ourselves, are there, you know, is this vector like contained among these degrees of freedom? So we don't expect this to be possible, but maybe it is, right? It could be. Let's try to solve the system. So I'm going to start by swapping rows 1 and 2. And then let's rewrite because we're not super pro as heck at this yet. And now we clear out that column. So I subtract row 1 from row 2 twice. So that means I'm adding this guy here. And I'm also adding 8, which gets me to 25. And then this is, I'm going to add 3 copies of row 1 to row 3, which will make this, I have to add -2, so this becomes -2. And then I have to add -4, so I get -10. And indeed, I can see that the bottom 2 rows can be simplified. 0, 1, 5. While I'm at it, 0, 1, 5. And then we have one step left, which is I should have to clear out this column since I have a leading 1. Oh, sorry, I was supposed to do math on that column. Let me recopy the middle row because it's the one that doesn't change. Now when I add this twice, I get a 0 here. And I add 10, so we get a 6 here. And then this becomes a row of zeros, which is at the bottom where it's supposed to be. So this represents A1 equals 6, A2 equals 5, right? Because this column is the A1s, this column is the A2s, 0 on the bottom. And so this says that it's possible, right? We succeeded in answering this question in the affirmative. 17 minus 4,2 is equal to 6v1 plus 5v2. Okay, I know these take a little while, but I don't want to just, axe this too quickly. I want to show also what happens if I pick something where it doesn't work. So let's just take this example and let's ask ourselves, what happens if I change it so that instead of that last equation, right, instead of asking about 17 negative 4, 2, I ask about 17 negative 4, 4. Let's just look at what changes, right? The first thing I want you to notice is every step of this calculation was motivated entirely by what's on the left here, right? The numbers that are along for the side, they're going to tell me the answer when I'm done, but all the math that I did was looking only at the left part. And so if I change this thing over here to a 4, This changes to a 4. And then the step that I did was I added row 1 to row 3 times. So if this number is bigger by 2, this number is also bigger by 2. And then when I divide by 2, this number is smaller by 1. And that means this number down here is also smaller by 1 because I subtracted. So now what we get is this last row says 0a1 plus 0a2 equals minus 1. Or in other words, 0 equals minus 1. This is just not true. So the upshot is 0 row equals non-zero number means no solutions. And that should make some amount of sense. What happened is we had two vectors that were spanning a plane. And then we had some third vector picked out that was in this plane. But then I increased the z component a little bit so that instead of being kind of flat in here, it was kind of going up like this. It's now outside of this plane. Does this make sense, the picture I'm kind of draw here? Since I elevated this vector, I kicked it out of the plane that it lived in, then there's no solutions. And we see that in the algebra by getting an impossible situation. 0 equals 1 is not valid algebra, of course. Okay, so that's kind of how we check whether or not things are inside spans of one another. Basically, the deal is you just do this Gauss-Jordan stuff applied to the vectors at hand. So what I recommend doing is start by writing down what you have, converting it to a system of equations, and then Gauss-Jordaning that. After you've done that a couple times, you will notice 2, 1, minus 3, 2, 1, minus 3, 1 minus 2, 4, 1 minus 2, 4, 17 minus 4, 2, 17 minus 4, 2. So in other words, what I'm saying here is that the process of setting this up, sorry, where did it go, is tantamount to extracting the vectors that you're dealing with and writing them as columns into this big box full of numbers. Okay, anything else that we should talk about in this video? Yes, there's one more thing I need you guys to know. I guess there are two more things that I need you guys to know. The first is, sorry, I got myself mixed up. What are the two things? Right, the first is a fact. Well, my phone is ringing. Well, too bad. We're going to have to deal with that later. The first is a fact, which is that, call this maybe a proposition. Span is the smallest vector subspace containing the given vectors. You can read this you can read the proof of this in Axler. I don't feel the need to regurgitate his proof because I don't think I have anything to add to it that really is insightful. The proof is kind of just unraveling the definitions. But this is a useful fact to know, so I want this to be in your heads as something that, I can definitively say that we emphasized. And the second thing I wanted to tell you is a definition. One more definition. A vector space is called finite dimensional when it has a finite spanning set. And what the actual dimension of a vector space is remains to be seen. Like, I'm not giving you a definition of dimension at this point in time. I just want you to sort of be aware of this notion that the vector spaces that we're considering are going to have finite spanning sets. And so I want to just sort of do a quick little compare and contrast. And so on one hand, any vector space like Rn or Cn is finite dimensional because you have the elements in them that look like this. right? And then we go on and so forth until you get to the one that's got a 1 in the last slot. Everything in Rn and Cn is clearly a combination of these vectors. Contrast with example 3, the collection, which we'll call by P of F, of polynomials with F coefficients. If you were an abstract algebra enjoyer last semester, we called this F adjoin X. This is not a finite dimensional space because, well, for example, if you give me any finite collection of polynomials, each of them has a degree. So, maybe we'll call degree of P1 equal to D1. I know I'm kind of running out of room here. Degree of Pn will be equal to Dn. Well, the issue is, because it's a finite list, if you just take the max of the Ds, let's call that just D for simplicity, the polynomial x to the D plus 1 power is not in the span of the P's, right? Because no linear combination using number multiplication can get you from that biggest degree to anything bigger than it. It's just too big. And so no finite collection can ever possibly do the trick for this. Okay, I think we've said enough at this point, so we're going to stop this here. We have to do the mirror side of the discussion, which is linear independence. And we will talk about that, probably next. So hang on to that thought, and I'll see you in a few.